Okay, so we were talking about the fact that in nickel batteries you have to have the same structure that is able to actually accommodate different oxidation states, but you have this tiny issue which is not inconsistent in nickel batteries, it's actually a limitation, that you will end up with the possibility, depending on the voltage that ends up applied, and if you have this overcharging, that not only you will have the exchange of electrochemistry that you want, which is fundamentally an electrochemistry on nickel, you will also push material inside the structure. But you know that you can push it out with enough effort, just that you don't have that effort usually with nickel batteries in operation. This process of reversible insertion of a guest into a host, especially for lamellar type of structure in which you have these layers, is called intercalation. So the request for a really nice intercalation is that you keep the characteristics of your host, so the structure of the host is fundamentally the same, but there is a degree of perturbation of the structure that might be like bond length and electron density that inevitably goes and changes into the physical properties that your structure can actually experience. So in order to have a nice intercalation process and to be able to do the intercalation, you need a very strong bond within the layer, so the intra-layer bond must be strong, and the inter-layer bond, so between two different layers, you have a weaker bonds. So this is something that we were already discussing when we already talked about bonding at the very first lecture. But if you remember how nickel oxide is set up, you have this very strong ball of nickel and oxygen within a layer, and the layers are separated a bit too much to have a very strong bonding. So they are interacting with each other, but they're not incredibly bonded like the covalent almost bond that you will have within the layer. So once you start inserting material inside, you can have like a third degree, second degree, and first degree type of staging of the intercalants. So you can even have one every 3, one every 2, or every layer occupied with an intercalating material in between. What kind of limits this process and plays the critical role? As usual, kinetics and thermodynamics. So you need to make the phase that needs to go inside in the right shape that needs it to go inside. So with water, fine, okay, you have it there, but you need to have the single molecule of water or a series of molecules of water that will go all in one way. Or if you have, like, for instance, potassium, you need a potassium ion that goes inside, not potassium. So you need to have the thing that needs to go inside in the right form, and then it will need to diffuse inside. So you have it, it needs to go in, so it kind of needs to shoulder its way in, and every time you try to you want to diffuse into another structure, so the guest into the host, there will be inevitably a level of expansion of the host to accommodate the new material that is going inside. Now this expansion is your energy penalty, so this will actually cost you effort to do. So if you need to know where is the most energetic effort for the structure, it will be in this point of the expansion. Why do you not start with every layer occupied? Because this energy penalty is reduced if you manage to do a staged type of intercalation. Because if you force 1 every 3, like this option here, then you don't have to expand the structure as much as if you were to immediately try to force the fact that every layer is to be occupied. So you kind of go in stages, because this compensates the thermodynamics of like the process that goes on. So on a regular basis, in your material, you will end up having some layers with intercalants and some layers without intercalants. If you have the right condition, you can push this process backwards. Of course, if you put energy into doing this, this might very well be spontaneous in another configuration, but you need these things to feel something. So to go in or go out, you must have something that is influencing the different processes. So it's not like you will not do it spontaneously each way. Decide yourself, and if you manage to put some energy or make it feel a potential, then this might very likely go two ways. Now that we know that it can go two ways, but nickel oxide hydroxide does it a bit weirdly, is it the only one that can actually do intercalation? The answer is clearly not. You have a lot of compounds that we call pillar clade. They're also called decalcogenides. They have all these like particular solid structure names, but the idea is always the same. The idea is that you have a very strong bond within the structure. So there is these titanium alloys in which something is very nicely bonded inside, but between the layers the occupancy is different, and you have like a series of stages. So here you usually have octahedral coordination of your atoms. These are very rigidly bonded. You cannot deform them because also you can see that they are connected by the edge of the octahedron, and sometimes they are connected with the whole face of the octahedron, so you cannot really move that. The stacking can change, and the intercalation is a function of how well can they accommodate something inside, depending on how they are layered and how much space there is in between. The something is also a function of like how much space do you have, because water has one size, other things have other sizes. And another thing that we already discussed plenty in terms of this thing is a layer structure are things like graphite. So you have very strong bonds of covalent nature almost of the carbon-carbon within the ring, but between the rings you only have the van der Waals forces, and this can be pushed apart, and this already influences the conductivity. We saw that the conductivity within the layer of graphite is orders of magnitude higher than the conductivity that goes interlayer. If you push something inside, it can intercalate, but it tends to go in very specific ratio, like 1 to 8, 1 to 10, 1 to 12, stuff like that. Not only because that's sort of like the graphite equivalent of the staged intercalation, but because the electron density within the layer is not really steady and even. And basically what you need is your intercalant, your guest, to find the right spot to sit down. So if you find one, likely it won't be the next one over, so you tend to arrange them spaced between each other, so you reduce the perturbation, and the bonding is actually better once you're there. Now, based on this concept, we can try to apply what is happening in terms of intercalation with the batteries that we know, and how could we possibly use this thing to make a new battery. So in an electrochemical cell, to begin with, we already saw that we want the cell to run spontaneously, at least on one side, possibly be reversible. But when we were talking about what do you want to optimize, what is the thing you want to do better, at the end of the day, always came back to the voltage. And given the voltage will be a function of how much intensity of current you are able to pass through your cell. So if you want a very high performance battery, you need a battery that works at higher voltage and is capable of giving you way more energy per unit volume than anything else. So this thing, which you might have seen also in the previous the previous task when you explore the learning goals, is an open circuit. So when you just have your components, what is the voltage that this thing will theoretically have? Now, this thing takes away all those problems of contacts, potential, over voltage, over potential, the fact that you actually need to make the current flow. This is just the correlation of your materials that gives you the way you should be able to go donor, acceptor, anode and cathode and chain them together. The open circuit voltage is depending on the potential, the chemical potential of the anode, the chemical potential of the cathode, and the charge. The charge are passing here is the electrons, but could be other stuff, right? So they already need to be chained this way. So the anode will be higher than the cathode because your anode is the reductant and your cathode is the oxidant. So they need to have a difference in energy that will make them feel the potential, otherwise there will be no drive for the electrochemical reaction to go forward. And then, since we have, they are not within the same material, they are two different materials and something that connects them in between, you will have the electrolyte in between, and the electrolyte being a sort of molecule or like a solution of something, will have by itself a HOMO and LUMO and a gap in between. Now, the issue is that you want to do electrochemistry between anode and cathode. The electrolyte is supposed to be the thing that drives your stuff around. So it is important that the chemical potential of the anode is lower than the LUMO of the electrolyte, because if it's higher, it's the electrolyte that is getting reduced, and that the chemical potential of the cathode is higher than the HOMO of the LUMO, because if it's lower, then the electrolyte gets oxidized. So it is important that you do electrochemistry on your materials, anode and cathode. You don't do electrochemistry on the electrolyte, because that thing is not going to give you any type of electricity. So in the nickel-cadmium battery that we saw before, but this thing could easily apply also to the nickel metal hydride, it's not a problem. You have your nickel oxide, which is our thing that is staged, and by nature of the fact that nickel can change the oxidation state, you can take more electrons in and rearrange this sort of staging that you have of the hydroxide inside. So if you assume that this thing can go in a range between 0 to 1, then you go from 3 to 2, that's your redox couple, and that will be the cathode. So the couple, so those are the final levels of valence electrons of your nickel. So you can go nickel 2, nickel 3, depending on the nickel 3, nickel 2, depending on the occupancy of those orbital. But that's the level of chemical potential that you're using. And then this will match the aqueous electrolyte, in which you want to look at the HOMO of O2 H2O, basically. And instead the cathode on the other side will have to get the electrons in and transform into an hydroxide type of stuff. So this will be your anode, and the chemical potential of this, so this is cadmium to cadmium 2+, so cadmium 0 to cadmium 2+, will have to match the H2H2O couple of the electrolyte. Because if you don't, so if they are not matched, you end up doing electrochemistry on water, which is not what you want. You want water to just facilitate this process. With an aqueous solution, inevitably, since we were talking about you don't want to do electrochemistry on your electrolyte, it means that the only energies that you can have are the ones that are limited by this window. So the window of the electrolyte is the limitation of the voltage energy, because at the end of the day, your the real performance of your battery, which is the open circuit voltage potential, will be from the top of the cathode to the anode, and this thing is limited by how well is your electrolyte opening around. Because if I were to find two materials that are chained in a way that makes them much larger than this point in between, sure, they should be able to do electrochemistry, but not with an aqueous electrolyte. If you do it with an aqueous electrolyte, your aqueous electrolyte becomes your limitation. So if we want to move the gap, so we want to do electrochemistry on materials in a way that allows us for more voltage and a battery that performs better, you need something that is capable of having a larger energy density and a larger voltage, so meaning that it passes more charge per unit of volume at a higher voltage, and since the voltage of the water electrolyte is already limited, you must move away from an aqueous electrolyte. So if something needs water to be carried around, it's not your thing. You want something that will be soluble in potentially something organic, something non-aqueous. And the answer to all of this business tends to be lithium ion. So the lithium batteries were tested at the beginning with like just a single unreversible electrode. So if you have your anode made of lithium and your material made of liquid carbonates, you have the chemical potential of the lithium, the window in the carbonates, so lithium salts of like dimethyl, diethyl carbonates, will be like 3 electron volt. The total window of this thing will go to 4.3 electron volt. Immediately double what you could have before. Why are you using dimethyl and diethyl carbonates as your electrolytes? Because they are able to catch the lithium and carry it somewhere else. If this weren't to be able to dissolve lithium, then when you do the reaction and you create lithium plus, it's impossible to bring it out and you cannot do electrochemistry. So this thing was first tested as an anode displacement reaction. So this is non-rechargeable. You just spit lithium ions out in solution of the electrolyte until you completely consume your lithium plate of metal, and that's it. Now this thing of having ethylene carbonate is also useful because you can notice here that we are not exactly in the condition that we said before. We were supposed to be upside down here, right? So this in theory could potentially destabilize the electrolyte. You could end up having weird arrangements in which the electrochemistry also happens on the electrolyte, but if you have the possibility of passivating your metal, then the potential that your electrolyte feels is different, and it brings you back into that business of higher than the anode, lower than the cathode. In this case, the cathode is not really there. So this thing ends up being the solid electrolyte interface. So it's sort of like a little cake of layers. So the first thing is this sort of tiny layer of inorganic lithium carbonates, lithium salt, stuff like that. You can transport lithium through, so the lithium plus can actually go in and out of these salts because they can partially dissociates. You can actually bring it out, so the mass transport is allowed. The electrons are blocked, which is very important because your electrolyte must not conduct electricity. And then the rest of this thing ends up being organic dilithium ethylene glycol, and it's nice and it can actually drag your lithium around and bring it potentially to another side. So this thing changes slightly the potential of your anode because it's a passivation layer, so it imposes a difference of chemical potential, which will go into a difference of potential of your material. So the solid electrolyte interface can be potentially problematic, but in this case it's something that you actually want to be able to operate your material properly. Now, as we were saying, this thing is an anode displacement, so this is just figuring out lithium and an organic electrolyte, but it doesn't have the other side. So this is not the full battery, let alone a rechargeable battery. Now, the first attempt with rechargeable battery has been done on the basis of that process of intercalation that we were discussing before. So since lithium is very tiny, it is very well suited to enter this sort of layer structure in between the layers. So in the first attempt to a rechargeable lithium-ion battery, you will have on one side the lithium, fair enough, and on the other side this titanium sulfide. And this was not super recent technology, 1980, and this will give you a 2.2 volt potential, but completely without water. And you will have these two reactions, so it's lithium to lithium plus, spitting out electrons and leaving behind lithium that doesn't have all the lithium it needs on the surface. And on the other side, you will catch a lithium plus. The lithium plus will go inside the structure, and you will move your titanium disulfide into lithium titanium disulfate, assuming that you can have a full solid solution of lithium, so the lithium can go from 0 to 100%, then the voltage of your cell is this modification of the Nernst equation, in which instead of having those activities, you literally have the concentration of lithium in the solid solution, and that's it. So going in, going out. If this thing is stable between 0 and 1, that's your full potential of the cell. Intermediate points will give you intermediate potentials. Here your redox couple is the titanium 3, titanium 4. So it's that level that you're playing around. The charged state, so when the battery can perform best, so when before you put it in, before you started, the most stored energy is when you have titanium disulfide. When it's completely discharged, so it cannot go any further, it's lithium titanium sulfate. So when lithium is 1, then your battery needs to be recharged. It's nice, the reaction is reversible. So if in this case, so when you connect, the cell performs spontaneously, so it spontaneously feels the potential and starts to put lithium inside the layer structure and creates electron in the process. If you then give it a potential, so you apply the difference in potential to the battery by plugging your charger fundamentally, then it will go the other way around. It will spit the lithium out and it will bring it back to the main lithium metal to reform your stuff. Nice, reversible. 1000 cycles with 0.05% loss of capacity, very nice. So really using solid against electrochemistry within the solid, amazing. But the recharging, so the moment when the lithium goes back, lithium plus goes back into the lithium and should reform this thing by having the electrons given, is non-uniform. By nature of not being uniform, it can form some very weird stuff, and this is the infamous reason why this thing is not the way we do batteries. It has a severe risk of catching fire, so you do not use this. So it was a very nice proof of concept in the 1980s, but it was basically shelved away from actual use for proper technology because it's unstable. So you risk fires, you don't want to do this. Now, what can we possibly improve in this thing? This is the layout of our cell. So we have the energy of the lithium plus couple, and then we're doing electrochemistry on the titanium 3, titanium 4 3D orbitals, the T2G 3D orbitals, given the coordination of this thing. And this is the thing that imposes your voltage limit. You want to stay here within these couples. We know that the recharging is unstable, so lithium as a metal should not work, but we were discussing the fact that intercalation of lithium, if it's a thing on one side, why can't it be a thing on another side? So lithium can actually be intercalated in graphite, usually in lithium C6 ratio. So it's a very precise way to do this. So C6 looks like this, then you could have C12, or this is just a normal graphite, because he wants to go in very specific positions, as we were discussing before. And this modifies your voltage, and since it's an intercalation, it's not on a surface of a metal, it reduces your problem. So it has a slowly lower electrochemical potential. It's reversible, so you can bring it back and forth, but you need to be careful with the charging, so you need to put more voltage on charging, because unlike having a whole surface of a metal available to put the lithium back in, here you need to do that intercalation process that requires some energy and requires some patience to happen. So on a crystalline level, so if you were to have purely crystalline graphite, this thing is actually a very huge thermodynamic limit, so you will have to put too much voltage to recharge the battery. The way to get around it was to make a material not perfectly crystalline. So this thing is fundamentally a bit amorphous, and by being fundamentally a bit amorphous, you don't have to worry about which side of the crystal you're exposing, and it's easier to push the lithium back in. So the improved stability is obtained by pushing down the potential of the anode with using graphite and intercalated lithium instead of just lithium. But then you have this other side. So what do we do on the other side? Now, for the optimal performance, as we were saying, we need a big gap between these energies. So very big, as big as we can possibly make it, because that will be your voltage, assuming that your electrolyte can actually withstanding. The issue in the image that we saw before is that the titanium and the titanium band and the sulfur band were very close to each other, like 0.1 electron volt close. So it's way too easy to end up in the sulfur band. You do not want to do electrochemistry on sulfur, you want to do electrochemistry on the titanium. So the trick that was taught at this point was, but wait a second, we have the periodic table. We know that the energy of the p orbitals, the 2p orbitals of oxygen, is significantly lower than the one of the 3p orbitals of sulfur. So we can increase the voltage by making something that is not a sulfide, it's an oxide. So same arrangement, fundamentally speaking, but with oxide instead of sulfur here. Note that in this case, so whereas when we saw the structure of titanium disulfide, there was nothing in between the layers. Oxides don't make the form in which there is nothing between the layers. So first resistance here was the idea that, oh, we cannot make the oxides because they don't make the pillared clay with the space in between. But the improvement that was taught here was, well, if you can put lithium directly inside, then this thing is your cathode in a fully discharged state, but it works if then you can push the lithium out. So these were the first structures attempted. So in these blocks, you either have nickel, octahedron, chromium, cobalt, manganese, octahedron, and in between you always have lithium. Now, issue with the nickel is that this structure is not stable all the way through. With the chromium, within the octahedron, given the energies of this thing, you can get the disproportionation inside the octahedron. So your own material is doing electrochemistry with itself, So it's disproportionating chromium 4 into chromium 3 and chromium 4, but this is not what you want. You want your material to do electrochemistry within the battery, so fine, not this one. These two, though, they're nice. So this, we can actually do this, and we want to form these structures this way. So this thing is important when they're like in orthorhombic or monoclinic, because you have these nice layers. There is some applicability of the spinels. It's important that you manage to order this thing very well, but this can be done because cobalt and manganese have a size that is completely different from the size of lithium, so you do not have the risk of finding lithium in here. The lithium will always be in here. So with a very nice order, you get a very nice performance. This encountered some resistance because it was a charged, like a discharged cathode. That basically you connect your battery, in itself is discharged. You need to recharge it at the first cycle and then let it run. But this is the way, when we go from sulphides to oxide, that we fundamentally change the energy landscape. So we moved away from the sulfide. The 2p band of the oxygen is significantly lower, and you can have access to redox couples that in a sulfides will not be touchable. In a sulfides you had titanium because it was higher. If you had cobalt sulfate, that's useless. You cannot access this as your higher energy state to do the redox couple. You will start doing redox on the sulfides. This is a huge bridge of voltage limits. It opens to a voltage limit of 4 electron volt or more, chained with a graphite electrode. Amazing. The last arrangement was making sure that now you have these materials that you know how to put in between. You know how to arrange your electrolyte. So the first thing is to remember is that if the anode and the cathode touch in any way, you short circuit the cell. The cell is not operational anymore. You're not doing electrochemistry. So a separator, it's an important thing to have in between, and the important stuff is that it's permeable to the electrolyte, and it's permeable especially to the lithium plus that needs to pass through. So it needs to be there, nice, separating the two materials, but still permeable, very thin. And potentially this is your safety point against overheating, because since we want it porous, if we have a battery that is overheating and you melt the separator will basically stop the lithium plus from flowing. If you stop the lithium plus from flowing, then your battery stops working. So fine, nice. You have a fail-safe for which your battery, if it's overheating, it will not keep overheating because you stop the electrochemical reaction and you put it back at the equilibrium where it was at that level. The electrolyte, you tend to have this lithium like chlorate type of stuff in propylene carbonate. Nice, vaguely unstable, so they can catch fire by themselves, not that fun. So they were later substituted by the fluorides, dissolved in this mixture of the carbonate compounds. Once again, ethylene carbonates was the trick, the solid electrolyte interface, which is nice and in between, and it ends up between your graphite with stuff. It protects the material from the decomposition and sort of like keeps the flow of lithium, but it's permeable at the passage of lithium plus, so it just goes through, but it gives a point of access for which first you need to diffuse there and then into the graphite instead of forcing through the graphite immediately. So this was the design of the first lithium-ion battery. So you have a cobalt oxide cathode, which are the most common and the most like state-of-the-art, traditional almost used. A petroleum coke with lithium inside. These two things are chained by a reversible intercalation and de-intercalation process. So the thing that is traveling around in terms of mass transport is the lithium plus, when your battery is charged, your petroleum petroleum coke is full of lithium plus. When you connect it, it fills the potential, and the lithium plus starts to flow out of the petroleum coke through the separator, carried by this organic electrolyte, and into your layered oxide. When your layered oxide has completely filled all the space between the planes with lithium, the battery has discharged, so there is no more electrochemical energy to be harvested. You can impose a voltage, so you use power to recharge the battery and invert the whole flow. And then this can go on and on and on and on with 4 volts of energy and a very densely, very light battery. So this was revolutionary. Acknowledged by the fact that Stanley Whittingham, who was the first guy who did the titanium sulfide battery, so he was the first guy that thought about using lithium ion. John Goodenough, who's the guru of any material that ever walked the earth in terms of transition metal oxides, so his group was the one working on transition metal oxide cathode materials and a series of other energy materials. And Akira Yoshino, who was the one that rearranged the intercalation in graphite, making with petroleum coke, optimize this whole device. These 3 people have been recognized in 2019 with the Nobel Prize in Chemistry, which is a very, as you can notice, solid state chemistry prize. So this was one of the biggest inventions of the 21st century as far as everyone is fundamentally concerned, and we're having this conversation because your computer is charged, so and based on this is the current design, and then in the last part we are going to touch on some perspective that you can actually have to further improve lithium-ion batteries.